Hello, welcome to 5.4, Properties and Applications of Logarithms. So properties of logarithms. In the following, assume that a, the logarithmic base, is a fixed positive real number not equal to 1, just like we saw in exponentials, and that x and y represent positive real numbers, and that r represents any real number. Here I had a problem with the scripting. So, first thing, log base a, that's our base, of xy equals log base a of x plus log base a of y. So the a is the base in these cases. The point of it, not to get hung up on my typos, is to realize that if you're doing log of a product, you can split it up into log of the first thing plus log of the second thing. Log of the product is the sum of the logs. You can go the other direction with that too. Log base a of x over y is log base a of x minus log base a of y. So the log of a quotient is a difference of logs. Now this one I talked about in the last section, log base a of x to the r. The r can come out front. That's r times log base a of x. The log of something raised to a power is that power times the log. Use the properties of logarithms to expand the following expressions as much as possible. Simplify any numerical expressions that can be evaluated without a calculator. So here we have natural log of x squared y over 3. This could be written as natural log of x squared y minus natural log of 3. That would be the natural log of x squared plus natural log of y minus natural log of 3. And this power can go out front. 2 times natural log of x plus natural log of y minus natural log of 3. Now, of course, 3 is just a number. Natural log of 3 is a number. Next one, log base 6 of the cube root of p squared over q. So treat this as log base 6 of p squared over q to the 1/3 power. This is like saying, you have a couple ways to go about this. I'm going to give this power to these first and then pull it out at the end. You could pull it out now. Log base 6 of p to the 2/3 over q to the 1/3. That's log base 6 of p to the 2/3 minus log base 6 of q to the 1/3, which would become 2/3 log base 6 of p minus 1/3 log base 6. That's log, not log. Log base 6 of q to the 1/3. There we go. Oh, look at this last one. This is the common log of 100,000 to the 2x. So treat this as the common log of 2x times common log of 100,000. Now, I just brought this power out front. Now, common log of 100,000, 10 to what power is 100,000? That's going to be 10 to the 5. 10 to the 5th power is 100,000. So common log of 100,000 is 5. So this is going to be the common log of 10x. Now that's going to be common log of 10 plus common log of x. Common log of 10 is 1. 10 to the 1 is 1 plus the common log of x. Okay, I'm going to go on to the next one. Feel free to pause that. So use the property of logarithms to condense the following expression as much as possible, writing each answer as a single term with a coefficient of 1. So we're going to collapse these. We have log base 5 of x squared minus 25 minus log base 5 of x minus 5. That would be log base 5 of x squared minus 25 over x minus 5. Now we can factor that numerator. That become x minus 5 times x plus 5 over x minus 5. I should do absolute values here because the term inside the log has to be positive. Or I should say non-negative. And of course, x minus 5's divide out. So this becomes log base 5 of the absolute value of x plus 5. Next one, we have natural log of 3 minus natural log of p minus 2 natural log of q. So that's natural log of 3 minus natural log of p minus natural log of q squared. The 2 becomes a power. So this is natural log of 3. Now look at this. The p is part's being subtracted and so is the q over pq squared. Go on to the next one. Next page. Use the properties of logarithms to write each of the following as a single term that does not contain a logarithm. Okay, so notice this is 10 to the common log of y squared minus 3 times the common log of x. This is going to be 10 to the power common log of y squared minus common log of x cubed. That's 10 to the common log of y squared over x cubed. So now we have 10 to the power of common log, and that just cancels. So I'm going to write that in the next one. 10 to the common log of y squared over x cubed. This cancels and just leaves y squared over x cubed. And notice here we have a being raised to the power of log base a in both these cases. So this is a to the log base a of b plus this 4 can become a power. Log base a of the square root of a to the 4th. And we have to do that. We have to get these coefficients over before we can combine them. This is a to the log base a of b plus log base a. The square root of a to the 4th is a squared. Now I'm going to combine them. Log base a of b times a squared. That cancels. Leaves it be a squared or a squared b. However you'd like to leave the answer. Now earlier I talked to you about the change, I talked about taking the log in your calculator, and your calculator only really has 2 unless you have the TI Inspire or TI Inspire CAS. I don't know if any of the calculators like a Casio. I'm not sure what they have. I'm just pretty familiar with the TI line because I like them. Okay, the change of base formula says let a and b both be positive real numbers. Neither of them are equal to 1, and let x be a positive real number. So this is how you would find like log base 2 of something. Well, it's not in the calculator. So this is how you can do it. You could change the base. So log base b of x would be log base a of x over log base a of b. So there's the b right there. There's your x. This can be used to find logarithmic bases, logarithms of bases other than e or 10. That's natural log, common log. These are what's in the calculator. But using your calculator, log base b of x would be log base a of x over log base a of b, which is the common log of x over common log of b, or natural log of x over natural log of b. Evaluate the following logarithmic expressions to 2 decimal places. So here we have 2 times log base 1/3 of 5. This would be like 2 times natural log of 5 over natural log of 1/3. These are in the calculator. That's going to be negative 2.9299. This is log base 3 of 9, so you can do natural log of 9 over natural log of 3, which is 2. And we know this to be true because if we said 3 to what power makes 9, it'd be 2 in there. Okay, let's talk about some applications. Phf solutions. The pH of a solution is defined to be the negative common log of the H3O concentration. This is hydronium ion concentration in moles per liter. Solution with a pH less than 7 are said to be acidic, while those with a pH greater than 7 are said to be basic. Let's scroll this up. So one type of detergent, when added to neutral water with a pH of 7, results in a solution with hydronium ion concentration of 5.63 times 10 to the negative 4th times weaker than that of water. What is the pH of the solution? Now, water has a pH of 7. It's neutral. So we'll do 7 minus the common log of our 5.63 times 10 to the negative 4th power. That's going to be 7 minus negative 3.249, which becomes 7 plus 3.249, which is 10.249. We're going to go on to the next page. Earthquake intensity. Earthquake intensity is measured on the Richter scale. You've heard about the Richter scale, named after the American seismologist Charles Richter. In the formula that follows, I sub 0 is the initial or the intensity of a just discernible earthquake. I is the intensity of the earthquake being analyzed, and R is a ranking on the Richter scale. So the ranking on the Richter scale is common log of I over I sub 0. By this measure earthquakes that range smaller with R less than 4.5, moderate 4.5 to 5.5, large 5.5 to 6.5, major is 6.5 to 7.5, and finally the greatest is 7.5. Okay. Northridge, 1994 Northridge, California earthquake measures 6.7 on the Richter scale. What was the intensity relative to a 0 level earthquake of this event? So we do R equals common log of I over I naught. We want to compare it to this, the intensity. That's 6.7 equals the common log of I over I naught. So raise both sides, making powers of 10. 10 to the 6.7 equals 10 to the common log of I over I naught. Anyone know why we had to raise both sides as powers of 10? That's because this is a common log and its base is 10. So that undoes it. So 10 to the 6.7 equals I over I naught. We want to solve for I, so I equals 10 to the 6.7 times I naught. And that would be 5,011,872.3 times the intensity of a barely discernible earthquake. That's how much more powerful that one was. I was in Southern California when that one happened. Not in Northridge, though. It's about 30 or so miles east of that. Okay, one more problem to do in this section. Decibels. Oh, I live with this one all the time. Typically measure sound in decibels. and you need a decibel meter, like when your neighbor has their music up too loud, you can tell the police, hey, the decibels or whatever. Okay, in the decibel formula, it follows I sub 0 is the intensity of a just discernible sound, just like I sub 0 in the previous problem. And the application was a barely discernible earthquake. I is the intensity of the sound being analyzed, and D is the decibel level. So here D equals 10 times log of I over I naught. Decibel levels range from 0 for a barely discernible sound to 40 for the level of a normal conversation to 80 for heavy traffic, 120 for a loud rock concert, and finally, as far as humans are concerned, around 160, at which point the eardrum is likely to rupture. Construction worker operating a jackhammer would experience a noise with an intensity of 20 watts per meter squared if it weren't for ear protection. Given that this should be I sub 0 equals 10 to the negative 12 watts per meter squared, what is the decibel level for such a noise? The decibel level is going to be 10 times the common log of 20 over 10 to the negative 12. It's going to be 10 times the common log of let's check it. Those are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 zeros there. I got that right. This would be 133 decibels. So we're in that range between destroying the eardrum completely and destroying it because of your the loud rock concert. So above a loud rock concert. Okay, that'll do it for 5.4, properties and applications of logarithms. Hope you enjoyed that. Thank you. Some of your questions.